Okay, good morning. Last week, we stopped here, and the exercise is related to the pipe band. And as we know, the pipe band we have additional inner pressures along the control surface, and for the inflow side and the outflow side. Okay, and then as I mentioned and summarized in this slide, we have the final exercise is associated with the stationary control volumes is a non-uniform velocity profile. So because it is the flow condition under non-uniform flow, so we need to apply integration operator to deal the problems. So again, we just look at the table, summarize how can we deal the momentum equation with the integration operators. So we integrate along the control surface and integrate along the control volume and integrate along the control surface. But most of the problems we assume the momentum changes in the control volume can be neglected. So we only focus on the net momentum flow and the sum of the external force. Okay, so let's look at the exercise. And the exercise we discuss with the drag force at the bullet shape device may be measured using a wind channel. And the tunnel is round of a diameter 1 meter. So we have we summarize some parameter in here. The D is the 1 meter, and the pressure at section 1 is the 1.5 kilopar. So the section 1 is the left hand side. So it's the inner flow. For the P1 is the 1.5 kilopar. And the pressure at the section 2 is 1 kilopar. So the P2 is 1 kilopar. All of the pressure are gauge pressure. And the air, the fluid material is the air, and the density is the 1 kilogram per meter cubic. And we know that at the inlet, the velocity is uniform with a magnitude 30 meter per second. So we have the V1 is equal to the 30 meter per second, and at the east, the velocity is non-uniform velocity. As sketched in here, it is not the uniform velocity. So please determine the drag force. Please determine the drag force on the device and the support fans. And in that question, neglect the viscosity resistance as the wall, and assume the pressure is the uniform across section 1 and section 2. Okay, so the first we need to deal the problem with the momentum equations. Consider the non-uniform flow. Use the integration operator. So that the right hand side we summarize, we assume the velocity function v2 can be represented by the v1 multiplied the k parameters and multiply the radial ratios. Okay, so and first we know that the question is satisfy the continuity equation. So the continuity equation tells us the Q1 will be equal to the Q2. So we write down the equation is the V1 multiplied the A1, because the V1 is the uniform velocity, will equal to the integration problems with the V2 and integrate the D along the dA. And then we know that the V can be represented by the V1 and the unknown parameter K, and the R is the radius. The radius is start from at the center and to the wall. This is the radius, and we can know that the R divided the R0, and the dA can be replaced by the 2 pi R dr. Okay, and the integration interval is start from the center to the wall, is a radius R0. Okay, so we can reorganize the equation of V1 and the A1, and this is equal to, we put some constant value outside the integration, so it's a 2 pi and the V1 and the R0 and multiply the K, and we have the integration start from 0 to R0, and the inside we only have the R squared and the dr. So we cancel out some parameter both sides, the V1. Okay, and then we know that the A1, what's the A1? The A1 is equal to the area, and the area are the same both sides in inflow and outflow. So the A1 is the pi R0 squared. Okay, will equal to the 2 pi and the K divided R0, and then we integrate the problems, so it's equal to a 3 over R cubic power, and then we put the R0 inside the integration result, so that will equal to the R0 cubic. So we cancel out some parameter, it will be 2, and we remove the pi both sides, and they also cancel out R0 square. So finally we can conclude the K will equal to the 2 over 3. So this is the first, we based on the continuity, so we can know that the K coefficients. Okay, and here we may calculate the area. Okay, the area will equal to 4 over pi d squared, and will equal to the pi divided the 4 divided the 4. So that's the area equal to 0.785 meters squared. Okay, so that's a problem. We focus on the drag force on the device. So we go back to the momentum equation. The momentum equation can solve the problem is the sum of the external force will equal to the net momentum flow. So we based on the force diagram here, and we have a momentum diagrams, and our problem is only along the x directions. And we know that the support fan in here, we will have the support force acting around the control surface. So the external force will, and this is the wind tunnel. So we have an inner pressure on the left and on the right. Okay, the inner pressures at both sides, inlet and outlet. So the force balance, we first have the P1 multiply the area and minus the P2 multiply the area. And the support force we assume to the left, so minus Vs is the support force and will equal to the outflow momentums. We deal with we have the integrations, and we have the V2 velocity multiply the low V2, and we do the integrations along the area, and minus the inflow momentums is the mass rate multiply the V1. Okay, so we can deal the problem step by step. So the first one, we can calculate this is our equation 1, and we have the mass rate, and we know that the mass rate is equal to the rho a v, and we use the v1 here. So we know that the density is the 1 kilogram per meter cubic, and the area is 0.785 meter square, and the velocity is uniform velocity is 30 meter per second. So we can calculate the mass flow rate is equal to 0.785 multiplied 30. So it's 3.55 kilograms per second. And we have the mass rate and multiply the V1, so we can calculate the momentum changes in the inlet. So also multiply the V1, so that will equal to 706.5 Newton. Okay, so we have additional answer in here. And the second, we deal the integration problems to calculate the outflow momentum changes. And so it's an integrate, we have the V2. V2 is the function to the V1, and okay, maybe I rewrite the equation to be we have the integration and the density, and we have a V2 square and the dA problem. So we take the density outside, and then we replace the V2 is the V1 square, and the coefficient K to be the 2/3 and the square, and here is the R square and the R0 square. This is the V2 square, and the dA to be the 2 pi R dr and the integration interval is from 0 to R0. And then we just reorganize the equations. So we put some constant value outside is equal to the 4/9, and we have a low density, and the V1 squared, and we have the 2 pi and R0 squared, and the inside we only have R qubit power d r. Okay, so it will equal to 2/9, and the density, and the V1 squared, and we have the pi, and R0 square over 1, and do the integration problem will equal to 4/0 4 powers. So we can cancel out the square R0 to be the 2. Okay, so finally this will equal to the A/over 9, and the density low, and the V1 square pi multiply the R0 square. So we put all of the number inside here. So A/9 multiply the density is the 1, and the V1 is the 30 square, and the pi, and the R0 here is half the diameter, so it's 0.5 meter. So 0.5 meter. Okay, so we can use the calculator to compute the answer in here. 9 divided the 8 multiply the 30 2 times, and multiply the pi, and multiply 0.5 2 times. So that will equal to the 795.2 Newton. Okay, so final we still need to deal with the problem with the force. So we go back to see the equation 1. So the support force in here will equal to the P1 minus the P2 multiply the area. Okay, and then minus the integration velocity, the outflow momentum, plus the mass flow rate V1. Okay, and the P1 P2 in here, we put the number inside is 1500 minus the 1000, and the area in here is 0.785, and the minus the outflow momentum is 795.2, and the plus the 706.5. Okay, so we can calculate the final answer. The 500 multiply 0.785 minus the 795.2 plus the 706.5. So the supporting force is equal to the 303.8 Newton, and with the direction to be the left. The exercise also need to require answer the drag force in here. So we know that the drag force is the reaction force in here. So we have the same force magnitude, but the direction is going to right. Okay, so this is our final answer. So for this problem, we are our velocity on the outflow side is the non-uniform velocity. So we need to deal with the problem with the integration operator, and this is also have the inner pressure on both sides, on the left and on the right. So we need to consider the pressure inside. So the following class is we need to move to the problem with the moving CVs, and actually we have two conditions for the moving CV. One is the constant velocity, and another is the accelerating. Okay, so how different they are, it's depend on how can we choose the reference frame, because the control volume is moving, so we need to pick up the reference frame and then we can discuss the problem. And the reference frame usually we can divide it into the two parts, the inertial part and the non-inertial part. So in practical use, if our control volume moving with the constant velocity or stationary, and then we can we can pick up the reference frame on the our control volumes. We call that is the inertial reference frame, such as the point at the ground, which is stationary always. So we call that the inertial reference frame. So on non-inertial frame, that indicates the reference frame will accelerating. So we call that is a non-inertial reference frame. So usually most of the problem are simpler if the frame is fixed to the moving object. Okay. So that we just slide just emphasize again. When we discuss the problem with the moving object, we need to take care of the velocity items. As the equation showing here, the capital V, which is the velocity relatively to the control surface, and the small factor V in here is relatively to an inertial reference frame. So the velocity definition are differences. So if we look at the crossings and your crossings, the control volume is moving, so we need to take care of the different velocity items for our problems. Okay, so we have the exercise, and then you can understand how different they are and how can we apply the different reference frame to deal our problems. Okay, but today we still have the quiz, so I may stop here and move to the quiz, and